All right, so we're talking about work and energy. The first thing I want to make sure everybody's clear on is the unit that we use for work and energy. What's the unit for work and energy? The joule. Okay, the joule. Now here's what I want you to know. The word joule, we abbreviate it capital J. It's actually a much larger unit than just capital J. What a joule is equivalent to is a kilogram meter squared over second squared. Now we saw a very similar thing when we did force. What was the unit we used for force? Newton. And a Newton, I told you to be able to figure out what a Newton is, because the College Board on the AP exam, they want you to know what the units are. So anybody remember what a Newton is? I gave you a way to figure it out. Kilogram meter per second squared. So notice how similar these two units are. The only difference between them is in the joule we have meter squared, and in the Newton it's meter. Now just as a reminder, how are you going to remember? How do you remember what a Newton is equal to? F net equals what? MA. F equals MA. So what's mass? Kilograms. What's acceleration? Meter per second squared. There you go. You got it. Kilogram meter per second squared. Now you're going to do a very similar thing. If you're ever asked about what a joule is, all you got to do is look at one of the equations for either work or energy. So for example, on the handout that I gave you yesterday, I have the 3 forms of mechanical energy listed there. The first form of mechanical energy is kinetic, and if you don't have the equation memorized, you will, because you're going to use it over and over and over. Okay, the equation for kinetic is 1/2 mass times velocity squared. Okay, so what do we measure mass in? Kilograms. What do we measure velocity in? Meters per second, but then we square it, right? So this becomes kilogram meter squared over second squared. What is that? That's a joule. So kinetic energy is measured in joules. Okay, let's just do one more. The equation for potential energy of gravity, the equation is mgh. If you don't have that memorized, you will, because you're going to do it so often. Okay, again, mass is kilograms. What do we measure gravity in? Meter per second squared. And then h is vertical height above the 0 point. What would we measure height in? Meters. So this all simplifies to what? The joule. Kilogram meter squared over second squared. All right? That's the unit for work and energy. Now, let's just look here. So what I want to do in this lecture is I want you all to be solid on the basic definition of work. But while we're talking about units, let's just check the unit for work here. What should work be measured in? Joules. Work and energy both measured in joules. Okay, so again, we just said force. Now what's force? Force is the Newton, which is kilogram meter per second squared. Delta x is a displacement. So what do we measure displacement in? Meters. So we get, this all simplifies to kilogram meter squared over second squared, which is the joule. Okay, now guys, before I go over this definition of work, I want you to realize something. Is our work and energy, is it a coincidence that they have the same unit? It is not a coincidence that they have the same unit. Now, only the people sitting here in the room, because I'm recording this video, so at home you're not going to be able to see this if you're watching this. So you guys are privileged, because you're going to see. I'm going to give you a few examples. So here are a few examples of how work and energy are related. So look, I'm going to grab an object here. Let's see. I'm going to grab this box right here, this little thing right here. Now look, I am going to do work on this box. Ready? I am lifting the box, lifting it, lifting it. So if you're at home right now watching the video, all I'm doing is I'm lifting a box. I'm lifting a box. Ready? Now watch. Ready, set. Spaldo is doing work, doing work, doing work, doing work. Okay? Now, by the way, what's the equation for work? Look at the equation up here. Work equals force times displacement. Am I exerting a force on the box? Yes. Is there a displacement of the box? Yes. You multiply those two together, and that's the work done. But here's the connection I want you to see. I want you to recognize this. The work that I'm doing in lifting the box is going somewhere. Where is it going? Into mechanical energy. What type of energy is this gaining as I lift it? Potential. And not kinetic, because I'm lifting it at a constant speed. In order to gain kinetic, you'd have to be going faster, faster, faster. So when I lift the box like this, the work that I'm doing goes into potential of gravity. So I do 100 joules of work on the box. If I do 100 joules of work, the box should gain 100 joules of potential energy. Work and energy are like this. Whenever work is done, the energy of the object changes. All right, let's do another example. Who wants to go for a ride?
Oh, yeah.
Okay, Daniel, come here. All right, so now, Daniel.
I'm actually going for a ride.
Okay, so Daniel's sitting in the chair here, ready? Now look, Spaldo is again going to do work. So if you're watching this at home, what I'm about to do is I'm about to accelerate Daniel in my chair. Okay? Now ready? I'm going to do work on Daniel. Ready, Daniel?
Yes.
And you're going to accelerate. Okay, you ready? Don't be scared.
I'm not
Don't be scared. Okay? Are you scared?
a little bit.
Okay, don't be. Okay, ready? Set. Okay. Now, all right. Okay. Thank you. I know it's old. Now look. As I. So I want to make sure everybody gets this. Did I do work on the chair with Daniel in it? Yes. Let's just say I did 1,000 joules of work. If I did 1,000 joules of work on Daniel in the chair, where did that 1,000 joules of work go into? It's going to go into some form of energy. Did it go into potential energy? That would be if I pushed him up a hill. If I push Daniel up a hill, then he's gaining some potential energy. But did he go up a hill? No. So the work that I did, the 1,000 joules of work that I did, went where? Into kinetic, because he was going faster, faster, faster. Now, follow-up question, would you say that 100% of my work went into kinetic energy? No, because what also was there? Friction. Does friction add mechanical energy to a situation or remove it? Remove it. So probably if I did 1,000 joules of work on Daniel in the chair, probably 600 of it went into kinetic energy. The other 400 was stolen by friction. And what does friction do? Friction turns mechanical energy into heat energy. It goes into heat energy. Okay? So the whole point here, the whole point is simply work and energy are connected. When work is done, the energy of an object changes. Okay, now, let's talk about this. Okay. The basic equation for finding the work done by a force is work equals force multiplied by displacement. Now, there's something very, very important that you have to know about this equation. The thing to know about this equation is that when you use it, the force and the displacement must be parallel. They must be parallel to each other. Okay? Or another way of saying that is the force has to be parallel to the motion. All right, so let's look at this diagram here on the left. If you wanted to find the work done by this force right here, all you'd have to do is multiply it by the displacement. It's that easy because why? Because the force and the displacement are parallel. Now come over to this situation. If you wanted to find the work done by this force, could you just multiply it by the displacement? Because is the force parallel to the displacement? No. So what would you have to do in this case on the right here? You would have to multiply the displacement by the x component of the force, right? So you're solving for components again. That make sense? You got to use the component of the force that's parallel to the displacement. All right, so here is a little sample problem. Now, I'm going to give you guys like 4 minutes, and 3 of the 4 minutes will be spent copying this down. 1 of the 4 minutes is used to actually calculate it. These are super easy questions, but I just want to make sure everybody's solid on calculating work done by forces. The work done by the force of the pull, which is 20 newtons. The first question is, find the work that this 20 newton force does. Can you just take the 20 newtons and multiply by the displacement? Nope, because the 20 newtons is not parallel to the displacement. So what you have to do for calculation number 1, we'll call this the work done by the 20 newton force, W20, equals, so you're going to go cosine 35 times 20 newtons. So what does that give us? That gives us the x component of the 20 newton force, because that's parallel to the displacement. Oh, and let's mark the displacement on the diagram. The displacement is 15 meters. So we go x component of the 20 newton force times the 15 meters. Those are both parallel to each other, and we get positive 245 joules. Now, somewhere in your notes, I want you guys to write this down because this is super important. The sign convention for work. Sign conventions are real big in physics, so write this down. Sign convention for work. Positive work is work done in the direction of motion. Positive work is work done in the direction of motion. Negative work is work done opposite motion. That's really important. Okay, second calculation, the work done by friction. Now this is going to be a super easy calculation because notice that friction and the displacement are already parallel. Okay, so we're going to go negative 7 newtons. Now why did I make friction negative? Well look, to the right is plus, to the left is minus, so friction would be minus. Multiply it by 15 meters because it's already parallel to the motion, or to the displacement, and we get negative 105 joules. What does the negative tell us here? Opposite motion. The work of friction is against the motion. Okay, calculations 3 and 4, you can see the answer without even doing anything. Notice that the normal force, so question 3, what's the work done by the normal force? Well, what do we notice about this normal force? Is it parallel to the motion? No. Does it have a component that's parallel to the motion? Or is it completely perpendicular? It's completely perpendicular to the motion. So when you go work equals force times displacement, the force is going to be 0. Because what does that force have to be? It's got to be parallel to the motion. So the answer to question 3, the work done by the normal force will be 0. And then how about the work done by gravity? What do we notice about the force of gravity? It's perpendicular to the motion, so it does 0 work. Is that to say that gravity never does work? Does gravity never do work? Or can gravity do work? It can. Look, I got a Kleenex box in my hand. Ready? I'm going to drop the Kleenex box. Gravity just did work, right? Because which way did the Kleenex box move? Down. Which way was the force of gravity? Down. Is the force of gravity parallel to the displacement there? Yeah. So gravity can do work. Or dudes, just real quick, how about a ball rolling down a hill? Look. Or an object sliding down a hill. If an object slides down a hill, does gravity do work? Yeah, because look, you guys know how to do this now. You got mg down like that. the displacement is this way, right? Here's your displacement like that. Does mg have a component parallel to the displacement? Yeah, this component of mg is parallel to the displacement. Okay? So the key thing for work, force and displacement have to be parallel. Now, final thought, I'm going to wrap this up. I promise I'm almost done. Promise. Guys, what would be the net work done in this situation for this problem we just did? What would work net? Net just means total. Positive 140. So look, net work has a significance. If net work is done, what must be happening to the object? Is it staying at rest? Is it moving at constant velocity? Or is it speeding up? It's got to be speeding up. Okay, and let me show you a way to think about this. So we have a net work. Look, the basic equation for work is force times displacement. If you have a net work, well, what must this F be? The F must be net force, right? Times displacement. So work net is force net times displacement. Well, what does F net equal to? F net is equal to what? MA. So the thought process goes like this. If you have net work, that means you have a net force. If you have a net force, you have an acceleration. You get it? And then my closing thought is this. In my notes and in the book, you're going to see this equation. The net work done on an object will always equal the change in kinetic energy of the object. Work net will always equal change of kinetic. In fact, let's get somebody else in the chair. Who else wants to go in the chair? Come on. I'm blanking on you. I don't have a blanket here. What's your name? Caleb. Caleb, come here. All right, so Caleb's in the chair, man. Look at. So watch. We're talking about work net. Okay, so your ride, Caleb's not going to be as fun. You ready? Here we go. I'm going to push Caleb with a constant speed. Not going faster, not going slower. Not going faster, not going slower. Okay? All right, good. I pushed Caleb. Look, I pushed Caleb with a constant speed. So like here we go. This represents Caleb in the chair. This is moving with a constant velocity. Acceleration equals 0, right? So look, if I move Caleb with a constant speed, what is the change of kinetic going to be? 0, right? If something moves with a constant velocity, there's no change of kinetic energy. So what must the work net be? 0. Well, how is that possible when I was doing work on Caleb? You got to remember, so force of Spaldo, I was pushing Caleb to the right, but what else was doing work? Friction. So say I pushed him 10 meters like this, right? Are you guys getting this? Yeah. Look, the work, so in that case, if I push Caleb with a constant speed, the work done by the force of Spaldo is equal to the work done by friction. Right? Work net will always be equal to change of kinetic. Hey, what if the work of Spaldo, what if the work done by the force of Spaldo was bigger than the work done by friction? Then it'll speed up and you will have a change of kinetic.